Good evening from China and good morning, good afternoon from everywhere in the world. Welcome to today's Tactile, Use Talk, Connect the World and the Universe. First of all, I'm introduce myself as a host for today's session. My name is Wang. I'm currently an associate professor at Tsinghua University. I also worked at the National University of Singapore as an assistant and adjunct associate professor before. So my research area is also highly relevant to artificial intelligence. So I worked on this interdisciplinary research field of AI plus X, or AI for science and engineering. So originally I was trained as a chemical engineer, but I found that computer science and artificial intelligence have huge potential in a lot of engineering fields. Therefore, since almost 15 years ago, I started my journey as a PhD in this interdisciplinary field in California, and then moved to Imperial College to continue my research, and then started my career in Singapore in the US. Finally, in 2021, I returned to Tsinghua University to be a PI and associate professor to start up my smart system engineering group in China again to work on this multi-scale modeling and AI for science and engineering area. So we have a lot of this research outcome in this field, but also look forward to communicate more with experts from different domains. So today I'm very honored to chair the session and welcome all the audience from many different fields, including artificial intelligence, robotics, electrical engineering, and also a lot of these engineers like my background, and also scientists like chemistry, materials, and all these relevant fields, because AI is definitely the key word and the hot topic that could impact everyone's life and everyone's research. Today we are very honored to have three keynote speakers to start sharing their research and also the field overall. Professor Shiqi Wang from CTU, Professor Chang Liu from Peking University, and Professor Fang from Beijing University Post and Telecommunications. We have a little bit change of our research of our talks order because Professor Liu has some traffic jam because today is the first day of the May 1st holiday, so it's a lot of heavy traffic jams from work. So we may have a little change here. Me as a moderator, and also we have our most respected, lovely Professor Haixia Zhang as our panelist today. Okay, so without talking too much, let's start our scientific talk today. So the first speaker, Professor Shiqi Wang from City University of Hong Kong, has extensively rich publication profile and contributions to the field. I'm so impressed with his profile. So Shiqi received his PhD degree in computer application technology from Peking University in 2014. Excellent rising young researcher, but has extensive, large amount of contributions in the field. He's currently an associate professor of Department of Computer Science, CTU of Hong Kong, has proposed more than 70 technical proposals to ISO and PEG and so on. He authored or co-authored more than 300 referred journal articles and conference papers. His research interests include video compression, image video quality assessment, video coding, etc. And also a lot of awards. I won't list them all, but several best paper awards from all this IEEE conference and almost all the awards in the field. His co-authored article received the Best Student Paper Award before and also served as an associate editor for IEEE transactions on circuits and system for video technology and several others IEEE transactions. Today, Professor Wang will bring the talk on generative visual compression, promises and challenges. Let's warmly welcome the first speaker.
Thank you, Xiaonan. So I'm going to share my screen. So good morning, good afternoon, and good evening. So it's my great honor to be here to introduce our research on the generative compression. So basically, in the AI area, so generative models are very popular. So here I would like to introduce how these generative models could benefit basically very, very unique tasks. So which is image and video compression. So let's first introduce image and video compression. So basically, without image and video compression, so I should say that nowadays we don't have this kind of video streaming technologies, and basically we could not see or use this kind of technology as Zoom. So basically, the target of the video or image compression is given a bitrate target or given the resources that basically required in the kind of real world systems. So we would like to achieve the best ever quality. So for this kind of video. So in the history, so there are many kind of different kind of image and video coding standards, or we see the compression standards. So for example, nowadays in 2020, so basically the MPEG has the BBC standard, and also our country, so China has a own ABS standard. So basically, this kind of video compression technologies could define the how the digital videos could be represented, transmitted, stored, and even processed. So but actually when we work on these kind of technologies, we also face a lot of difficulties. So for example, basically when we work on the kind of these kind of standards, so most of them I should say that they follow this hybrid video coding framework. So basically, this hybrid video coding framework, they rely on the handcraft features. So for example, the prediction, the transform, the residue coding, and entropy coding. So nowadays, it's really, really difficult to improve this kind of coding performance of the coding tools. So we can see from this table, so basically for the state-of-the-art video coding standard, so for each one, so the performance improvement, so for each coding tool, the performance improvement is really between 1% and 2%. Here, 1% means that at the same of the visual quality, so basically we can reduce, for example, only 1% of the bitrate. Yeah, so this is the current status of the video coding standards or video coding technologies. So, but so basically we have today we have a lot of generative models, a lot of AI models. So we are asking ourselves a question: so whether we could use or kind of whether these models could benefit this kind of compression task. So we try one kind of very, very unique application, so which is image compression. So this image compression, why we see that as unique? Because it's image compression in a specific domain. So basically, our idea is very simple. So we want to decompose this image into different layers. So for example, we can decompose that as a structure layer and also the texture layer. So the structure layer is kind of like the edges and this kind of features from extracted from the handcraft extractors. And then we can compress that with a specific codec. And basically, we can also extract the textures. So, and also compress this kind of information based on the codec. And as a decoder side, so here we are introducing the generative coding. So as a decoder side, so we use the generative models to synthesize this image. So very interestingly, we find that, well, this kind of methodologies is really powerful in terms of the representation. So here we provide you one example compared to the state-of-the-art video coding standard, but we actually use intercoding for this BBC. And you can see that, well, from the same or similar bit rate, so or bit per pixel. So basically, this kind of generative method is achieve much better quality. So especially at very low bit rates compared to this kind of traditional standard. So basically, this is for image, and we are thinking that whether we could actually borrow this kind of similar ideas into this kind of video codec. So basically, we first analyze about the trends of the video codec. So we know that nowadays video are becoming very high definition, right? So we have high resolution, 4K, 8K resolutions. And also we know that, well, we have AI, this kind of very powerful prediction, very powerful representation technologies. And also, so traditionally, a lot of videos, we see that, well, that's the final receiver is human beings, but nowadays things change very differently. So we know that machines are replacing the humans as final receivers of these videos. So basically, how to represent these videos for machine vision, how to represent these videos, even nowadays, we know that large multimodality models also receive these images and videos to the analysis. So how we could optimize the whole video codec towards this kind of machine vision or towards both human and machine vision. So these are the future trends of the video codec, and based on these ideas, so we want to develop the a different kind of coding framework, coding method. So our compression method. So here we do the kind of analysis. So basically nowadays we know generative models are very popular, and we know that in this year we have this Sora model. So when Sora actually become a real kind of product, so it's very amazing, right? So we know a lot of news, right? So these are generative models. And basically at that time, so many friends asked me a question whether these Sora models could benefit your research, could benefit this kind of video compression. So the answer is yes, and the answer is no. The answer is yes, is do have some common sense. So basically, generative models aim to generate something, and also in video compression, we also will aim to come up with something that is actually kind of like a video. But the answer is no, because the task is totally different. So let's do the analysis. So generative models learn the underlying distributions, and basically it focuses on the generated quality. So here we see that, well, generated quality is in a very kind of a semantic level. So basically the semantic mean it's semantic meaningful, and also it obeys the physical law. So that's okay. But compression technologies, so basically we follow this traditional information theory, and actually we focus on this redistortion performance. And regarding this redistortion performance, so basically we have two dimensions. The first dimension is resources, for example, the rate. And also we even focus on the complexity and so on, for example, the delay. And another dimension is actually the distortion of the video, or basically we see the quality of the video. So basically, it's kind of like relevant, but totally different task. So how to design the kind of solutions based on the generative technologies for compression? So that's a question. So here I use very typical example. So generative models is kind of like the tiger, but compression is kind of like a cage. So why is a tiger and a cage? So basically, let's see here. So basically, we see that, well, generative models is big constraint. It means that as long as we achieve this kind of semantic level alignment, so that's fine. That's totally fine. But for compression technologies, it's very strong constraint, because we need the pixel level alignment, and also we need to consider the bit rate. So this is very, very different stories, but basically we see the generative models focus on the quality of the generated content, but compression techniques prioritize efficient representation, right? So based on the kind of bit rate, or we see that available bit rate, or we see that, well, based on the current available resources that could be provided for this kind of task. So basically, our question is how to bridge this generation and compression. So the answer is we use priors. So basically, we all know about the prior models, the statistical priors. So how to leverage these kind of priors is very important. So here we start from the face, because face have very strong priors, because we know that we have a limited number of emotions. So this is a human face. And also basically the human also have very strong prior, although not like the face. But the natural thing, so it's not that strong, but still it could provide us some priors. For example, when we are given a video. So based on the priors, we know that whether this video is from the real world, or this video is generated by this kind of AI models, or generated by this kind of graphical models. So these are the priors. So how to leverage these priors for this kind of compression task? So many years ago, even 70 years ago, so people answered this question. So we found out this paper and it's very amazing, but basically these 70 years, people did not develop this kind of product level approach based on this framework because we know that basically we don't have this very powerful generative techniques, but now we do have. So 70 years ago, so it's around this kind of this kind of time. So basically, people start to realize that we can analyze this video content and then synthesis the video content. Analyze happens at the encoder side, and synthesis happens at the decoder side. And in between, so we can transmit these parameters. So when we compress these parameters, so everything could be done in very elegant way. Although actually this framework is really, really beautiful, but at that time, so that I said, so basically it's not very robust towards different content. And also the generalization capability at that time is not, we see that, well, it's not good. So it means that at that time, so it's not because of the framework, but because of the models. So this kind of model-based coding technologies is not coming true. But nowadays, we know that, well, we have very, very powerful generative models. So a lot of generative models, I will not introduce that. So I just basically introduce the main idea. So basically, based on this kind of insights, so we developed the first one is generative video coding technology. So basically, we have two parts. The first part is we use the traditional video codec only for the key reference frame. And for the subsequent frames, so we all use the generative models to extract very, very complex features. And at the decoder side, we synthesis or generate the video content based on the deep neural network. So this is our main idea. And basically, you can see that this idea comes true because we have the traditional 70 years ago's framework, which is analyze and synthesis. And also we have today's very powerful generative models. So basically, this is our approach. So basically, at the encoder side, what we can do is we can analyze the video content, and based on the analyze result of the video content, so what we can do is we can compress these features, and then we can transmit these features to the decoder side. And the decoder will be very complicated because given this transmitted information, we can synthesize the video. So basically here we provide overall map of the decoder, how the decoder achieves this goal. So basically, for example, we have 2D landmarks. We can transmit 2D key points and 3D key point and also compile features. So basically, we develop the strategy based on the compile features because we know that in deep learning, in AI, so basically everything relies on the features. And basically, at the decoder side, based on these compiled features, we can have the dense flow, we can have the occlusion map, and basically we can use generative models, or we can train these generative models to generate the output video. So our approach is different from the traditional generative approach is because actually we are focusing on the rate distortion performance. We are not focusing only on the quality of the generative video because we focus on how many bits are used to represent this video. So basically, this is quite different from the traditional approach and the traditional generative approach. And basically, we have achieved some coding gains. So basically, this blue curve. So here we compared our approach with the state-of-the-art video coding standard. And as you can see that, well, this blue curve is the VVC standard. So VVC is actually the state-of-the-art standard in MPEG. So basically, as you can see that we can achieve more than 50 bit rate savings at the same level of the quality. So here we use two different coding measures, for example, DSTS and LPIPS, and basically we will discuss that. Well, there are still some problems how to evaluate the quality of the video. But anyway, so from this curve, so basically we can see that well, our performance is much better than this kind of state-of-the-art approach. And also we compare our approach with the other kind of solutions, such as NVIDIA's solutions. So basically, also achieve very good performance. And also here we provide you some visual quality comparisons. So basically, they are encoded at a very similar bit rate, and even our approach is lower bit rate. But as you can see, the first one is VVC result, so it's totally blurry, so people will not see the face. And the second one is actually in NVIDIA's solution, and basically the third one and also the fourth one are our solution. And also, we give you more examples for this kind of comparison, and also we put out these videos in the website, so basically everyone can download these videos for comparison. And basically, that's the first application. And second application for this generative method is basically we want to deploy this kind of philosophy in a totally different scenario. So which is for machine vision. So as you may know that, well, these kind of videos, these kind of images, the final consumer is not only human beings, because nowadays we know that machines have the capability to analyze the videos. So how to represent the videos for machine analysis? So the very straightforward way is actually we represent that based on the features instead of the testers. Because actually we know that machines rely on features for kind of analysis. So basically, we also developed the feature compression technologies in this work, and basically we divide this kind of representation into two layers. The first layer is the feature layer, so which means that basically in the first layer, or we say the base layer, so we only transmit the feature for analysis. But assuming that we have 10,000 streams, so we only interested in 10 streams of this analysis. So basically, we want to reconstruct these kind of images or videos at the decoder side after we checking that, well, they are of great interest to us. So basically here, we also can use these features to generate these kind of textures. And at the enhancement layer, we only transmit the signals, the kind of information that could not be well generated. So this is kind of a scalable approach, and basically it could support both the machine analysis and the human viewing. So basically it means that it's a kind of a collaborative machine and human interaction based on this kind of approach. And also the third one is we see that, well, we first define this interactive coding in metaverse. So basically, based on our generative-based compression approach, so basically what we do is we send the physical meanings or we incorporate the physical meanings in the base rate. So it means that traditionally, when we want to control something, so for example, we want to control the eye, we want to control the mouth, we want to control the height. So one way is actually we control that at the encoder side and then transmit that to the decoder side or receiver side. And another way is actually we only receive that at the receiver side, we reconstruct the video and then we apply these generative models to generate a video based on the reconstructed video. But our approach is quite different. So it's kind of like very green approach because we only added the base rate. So based on this bitstream level editing, we can do a lot of tasks without increasing any complexity. So basically, I would like to call this as the interactive coding framework. So basically, it have a ultra compact and also configurable and also thematically meaningful representation. So here we show you some examples as well. And the next one is actually when we propose these technologies in the standardization body, so there is one question. So whether if the encoder and decoder, they have some mismatch, so whether we can address this problem. So basically, we believe that, well, this is very, very interesting problem, and we developed the decoder adaptation approach. So based on the traditional idea of the trace coding in the traditional video coding standard, so we developed the first trace coding scheme for the generative video coding. So basically, the idea is very simple. So because in the language, so we know that even now we still have the translation, right? So basically, we can do this kind of translation. So, but how we going to do the translation at the feature level to enable so different kind of decoders and different encoders when they mismatch? So how we can incorporate this kind of transcoder or translator in between? So this is a problem that we address. And basically, when we propose this idea in the DCC conference, so basically also received some good feedback from the reviewers. And basically, here is something that I want to introduce about the promise, which means that we really perceive some promise and also performance improvement. But we know that there are many challenges and also opportunities along with these challenges. So the first one is standardization, because actually when we work on the video compression, so if we don't talk about the standardization, so it will never be used. So basically based on that, so basically we propose this into the GBAT. So basically who define the kind of standard. And basically for we have done this for more than 1 year, and some proposals we are lucky, so it's been adopted. And as far as I know, so this is the first kind of efforts to push this kind of generative coding method in this GBAT and also MPEG. So basically also receive very good feedback, and also more and more companies are working on this kind of technology. And also our platform has become the common software tools, and also we define this we with some collaborators, so we define this testing conditions, so for developing this kind of standardization efforts. And the next one is when we work on this research, so basically we find that, well, we still have some challenges. And the very important one is how to evaluate the quality of the reconstructed videos. Although actually we use LPIPS and DSTS, but we still perceive a lot of problems. So that's why actually we developed our own dataset, and we actually a lot of efforts in labeling this dataset, and basically this work has also been accepted in TMM so recently. So basically, I think this is also the first efforts. So merge the traditional compression method and also the learning-based compression method, the generative models, so together and develop a uniform dataset to address this problem. And also, actually, we are working on face video, and currently we are working on the human video. As human is actually more complicated than face, and but we really want to extend this kind of approach into the natural scene, because actually we know that natural scenes follow the natural scene statistics. Although it's really difficult, but we still believe that there should be some hope. So basically, from the very strong priors to even the amazing priors or big priors. So basically, how to leverage this kind of natural scene statistics. So to do this kind of task. So and also regarding the future coding, so basically we are working on this kind of generative coding. So from the signal level coding, and finally, I think the semantic coding is also very promising, especially for this cloud and collaborative computing, because basically nowadays the videos they have two receivers. The first one is human. Human is from perception to the memory, but also we have the like models. So for example, we have knowledge and also this kind of emerging capabilities. So here I would like to thank the collaborators, for example, Professor Dr. Ye from Alibaba, Professor Ma from PKU, and also the other collaborators, and also our students. So actually, they provide a lot of good suggestions to this this school and wisdom, so we can make this we can go further. So thank you very much. So thank you.
Excellent. Thank you for the first speaker and the excellent talk by Professor Wang.
Thank you.
Let's leave the discussion Q&A session to the end of the three talks. So thanks again. All right, let's move to the next speaker then. Since we changed the order a bit, so our next speaker is Professor Bin Fang from Beijing University of Post and Telecommunications. So let me first introduce Professor Fang with also a lot of achievements. So Professor Bin Fang has main research interests on intelligent perception, interaction, and operation of robots. He's also a Secretary General of the Cognitive Systems and Information Processing Committee of the Chinese Society for Artificial Intelligence, which he's also a distinguished member of Chinese Society for Artificial Intelligence, and executive member of the Intelligent Robots Committee, and also a EEE senior member. Has also published hundreds of publications on Nature Communications and IEEE and other conference papers, also with extensive amount of best paper awards from international conference and journals. I won't name them all, but a long list of awards and best papers. So Professor Fang used to be my colleague at Tsinghua University, also renowned professor, leading a lot of students' chapters and winning the championship in several international competitions, and was awarded the excellent instructor by Tsinghua University. Very welcome, popular professor at Tsinghua. He was also selected for National 13th Five-Year Plan Science and Technology Innovation Achievement Exhibition, and his autonomous swipe collection robot system won the silver medal at the International Geneva Invention Exhibition. He has also won several early career awards of IEEE communities, also Young Scientist Award of many societies. So without introducing too much, let's leave the time for Professor Fang to give us today's talk on the very hot topic on embodied tactile and robot GPT for manipulation. Welcome, Professor Fang.
Okay, thank you. Thank you for Professor Wang's introduction and Professor Zhang's invitation. Now I show my presentation. Okay, can you see? Okay, good evening, everyone, and it's great honor to share a part of my research work in this platform. And tonight I will give the presentation of embodied tactile and RobotGPT for manipulation. And my presentation will be divided into 4 parts. And about 5 years ago, in 2019, Professor Krajcik has been published a paper in Science, and she said that dexterous manipulation is one of the most challenging problems in robotics research. Of course, it including perception, plan control, mechanism, sensor, or skill learning. So it's complex, and we can find in recent years, especially the emergence of ChatGPT, the company like Microsoft, OpenAI, Tesla has been focused in robot manipulation, and they want to use ChatGPT to accelerate society into a robot age. But we can find that currently the robots rely heavily on vision-driven manipulations. So it only use vision, we think is not enough. We can find humans can operate skillfully by touch in dark environment. So how to improve our manipulation use Tactile is a great topic. And about 2 years ago, in Science Robotics, has been published a review that emphasized that Tactile is very important for robots, especially how to make a human-like skin or nervous system functions is also a important topic. So, how does Tactile drive general robot manipulation? Is a long question to research. So, I will introduce some research work about my Tactile to robot manipulation. So we can find that there are different mechanisms for tactile perception, like captive, receptive. They are electronic tactile sensors. But we can find the least mechanism of tactile sensor just has sparse information. And in recent years, vision-based tactile sensor has been a popular research and hot direction because the vision-based tactile sensor has the advantage like high resolution, simple structure, and also including abundant information. And we can see this tactile sensor with the high resolution of human eye and the sensitive of human skin. And we can find when we touch this sensor, we can capture the images of our of the tactile information. And in recent years, it has been a hotter research area. And like in ICRA or IRAS, the top conference in robots has been awarded like best paper, all including list related work. And nowadays, vision-based tactile sensor has been tended to develop integration, function, and miniaturization. And G-Sight is the most representative sensor. And I started to focus this research about 10 years ago. And this is my root of the research of the tactile sensor. And various of tactile sensors have been developed, like a fingertip or encrypted in pen or in the figure, in the figure. So I will introduce some my work about this tactile perception. And I'm the first group devoted into this research direction. So some best paper award has been awarded in about this research direction. And I have this sensor and divided into 3 models, including the contactor module, camera module, and the illumination module. So the structure is simple. So I'm in the computer department in Tsinghua, and I'm not in the mechanism department. So because of the simple structure, so the students in CS also can make this sensor. So with the simple structure, we can do more information and do more research in computing. And about 2 years ago, I have surveyed the hardware technology of tactile sensor, and we also went to everyone can design the earn tactile sensor. We according to our view, and now it also include the top 15 most frequent assessed paper in RGB sensor journal. And based on the research hardware technology, we also designed a process volume system, and it including the bioprocessing coding and the visualizer interface. So you can use this software to design and manufacture your own tactile vision-based tactile sensor, and now we introduced some recent work about our vision-based tactile sensor, and based on spring process and the metal sparring process, we have proposed a new coating preparation technology, and it's low cost, and the maintenance of the contact measure is improved. So with the metal foil procedure, the sensor can be thin and high sensitive of deformation, and this service enhanced process can make the sensor more durable. So we also compared our sensor to the other sensor like the famous G sites or the other omnitactile sensor or GSM or digit, and we can find the high resolution of our sensor can be shown in the figures. And then we also developed our sensor to be more durable, and the well drawing process has been proposed. With this design, we can provide a micron level tactile spatial resolution, and the well resistance is also being improved. So with this technology, we can provide high render tactile data, and we also use the equipment to show the details of our tactile images. We use the microscopic imaging, and we can find the coating particles can reach the nanometer levels with our well drawing process, and also we in order to improve the performance of our tactile sensor and the spatial resolution, we have used the millimeter scale, sub-millimeter scale, and micron scale, and we can find the tactile images can capture a micrometer level in detail. We also built a motion platform to test our performance, and like edges, balls, turbos, and to contact our sensor, and we can find the different shapes and in different forces. The sensor can capture and adapt different solutions of the sensor. Yeah, and we also implement the wear resistance of the coating, and the electron wear tester has been used, and we test more than 10,000 contact, and our sensor also can keep the the high quality of tactile images. So with this high performance of tactile sensor, it can be used in different solutions. And also we wanted to improve our tactile sensor to be more informations. Well, we can see if we drive the car in the night, the strength of light is very influenced of our sight. So we think if we use the transparent gel with our tactile sensor, so we can capture the outside images with our sensor. And if we tactile, we contact the near the sensor, so we can capture the tactile information. So with this mechanism, we can call it the total internal reflection with the outside and inside visual and tactile informations. Yeah, here is show the wait a moment. Sorry. Yeah. When we turn off the LEDs, and we can see the outside and the internal vision. And when we contact the transparent gel, and we can focus the tactile informations. So the different environments, we also can capture the different models. So we also sorry. Oh yeah, we also taste different fabrics, and we compared our TIR gel and the common vision-based tactile sensor, compare the performance, the different performance of these the two sensors, and we can find with our novel TIR gel sensor can get more result and more more accurate performance. Yeah, and we also integrated the vision-based tactile sensor into our soft hand pair, and the hand we developed with the jamming level structure and the tender structure, and the vision-based tactile sensor, it's a multimodal tactile sensor. It not only capture the force, but also the fabric and temperature. And with this multimodal information, we can not only grasping, but also perception the relevance of these items, so it can improve the average grasping success rate with our sensor. And also in experiments, we find if we just to equip the tactile sensor for learning, it is time confusion and consumable. And we think, and how to generate by simulation the tactile simulation is also a very important and a meaningful topic. So about 3 or 4 years ago, we focused to build a tactile simulation environment, and we use the Taiji. It's also an open software to simulate the elastic of the chair, and this paper is also published in ECM. And we built a simulator named Taichi, which generates the tactile images, and we also use this Taichi to integrated into the simulator of the robots like Pybullet and Gazebo, and we can find that the robot simulator can provide the real-time position or speed of sensor and contact objects. And the results show the great performance of our simulator. So with this tactile simulator, we can do more manipulation learning, and the tactile acquire has been cheap and convenient. So with this simulator, we has been focused some complex tasks like manipulate the plastic body. So with the deformable body, it is complex. So we first build the deformable simulation, and then we learning in this simulation, and then the policy transferred to the real environment. So with this idea, and we use the Taiji to simulate the software contact, and also we use the TR vision-based sensor to complete this task. And and we can find with this sim-to-real the task can be successfully completed, like to the sphere or silent, and with manipulation learning of deformable objects with our sensors. This work has been submitted to the HVTRO, and it's also under review. Yeah, and we also find that in especially emergency of ChatGPT, the robot large mode has been listed as an important development direction. So the robot integrated LM for built the robot large mode is also a hot topic, and because I always I'm focused on robot manipulation. So I'm also thinking how the what foundation models can bring for loop learning in manipulation. And I've paid more than half years to survey the direction, and this paper has been uploaded in the cave. And we also went to summarize the or a clear clue for the robot learning for manipulation. And we find nowadays the different larger models have been integrated in the robot for different tasks, like larger language models. The alternative is GPT-3, and the vision foundation models is same is from the metal, and also like vision larger mode or larger multimodal models. And also the famous robot foundation models is Google's RTX. And we also summarized the current state of research in a table, and we can find nowadays industry has a significant advantage over academic. So especially our college, how to revise or improve our research way. I think is also a very important question to thinking. Yeah, of course. In recent year, I focused the robot is different. It's different. The research of artificial intelligence. We thinking the robot in our real world is the safety and the reliable is are very important in our real environment. So if we directly use the ChatGPT to the robot manipulation, we think it's risk because the each output of the ChatGPT is unstable. So we need a more reliable framework for the robot manipulation. So I proposed the framework for robot manipulation learning from the ChatGPT, and with this framework, we can find it can significantly improve the task success rates, and with an average increase from the 24% to more than 90%. And yeah, and we also learning in the simulation and deployed in the real environment, and the different tasks has been implemented, like move curve, stacking, or house building, and we can find the like house building. It is an interesting demonstration or example for the ChatGPT to build the house, and with the example we can find the super performance with the large language model. Now we also has considered the three aspects to divide the task difficulty in three levels, and it's found that the task difficulty increased and the success rate decreased significantly. And our RobotGPT model shows the robust across all levels of tasks and maintain a good performance. We can find it can achieve 0.9, more than 0.9 on average. Yeah, we also designed a compared test, like a A/B test, and humans vs RobotGPT. And we also find that RobotGPT demonstrate the advantage in both code quality and time computing. Yeah, and we can find with the large language model has a super than common technical. Yeah, and also we can find some experiments like sorting or spelling some long word. Yeah, and we with the RobotGPT, it can give us a clear sorting. Yeah, and also we also thinking what about in future and the how to collect high quality multimodal data is also a very important question, and how to improve the general machine learning ability, and is also our trying to pursue the direction. And nowadays, the RobotGPT or larger language model has only the vision or language, but the tactile is amazing. So I think how to use tactile information and tactile driven artificial intelligence is also a new development point, and is also a greater future work we have to do. So and thank you for attention, and there are my presentation, and here is my email, and if you're interested in my work or you want to cooperation, please email. Thank you, Professor Wang. Okay.
Thank you for the excellent talk by Professor Fang. I've learned a lot. Really enjoy this recent progress. Audience interested, please read the latest publication Professor Fang shared on arXiv, very comprehensive review of the field. Thank you very much. Again, we will keep all the questions and answer to the last session after the next talk. All right.
Okay.
So, okay. Thank you again, Professor Fang. All right. So after the first two talks, let's move forward to the last speaker, Professor Chang Liu from Peking University. Professor Liu is also a rising star in the area of AI and robots. So he's currently an assistant professor in the College of Engineering at Peking University. He's a member of the National Youth Project of the Overseas Talents Program and of Beijing Nova Program. He received his bachelor degree from in electronic information science and technology and in mathematics, applied mathematics from Peking University, and a master degree in mechanical engineering in computer and also computer science, and a PhD in mechanical engineering from UC Berkeley, really interdisciplinary background. He was a postdoc associate at Cornell, and also worked at Ford Motor Company and NVIDIA Corporation on developing autonomous driving system. He has also won several Best Paper awards and served as area chair and the committee member for several world-renowned conferences. So today, Professor Liu will bring the talk on robot collaborative motion planning and active sensing. Welcome, Professor Liu.
Thank you very much, Professor Wang, for your introduction. So let me share my screen. Let me see if that works. Oops.
You can directly share your screen. Great, we can wait for a minute.
Okay, so can you see my slides?
Yes, we're clear.
Okay, cool. All right, thanks. Okay, so yeah, thank you very much for your introduction, and we're glad to be here today to share with you our work on robots. So basically today I'm going to talk about our recent work on active sensing and swarm motion planning. So basically I changed my title a little bit. The first question is, why do we care about these topics? I think the reason is pretty simple, because we know sensing and planning are the critical components for.
Hi, Chang. Sorry to interrupt. I think the slides are not moving. It shows this default layout. If you can show the
So let me
play mode,
figure it
it
out.
will be better.
Yeah. Let me see what happened. Let me share again. Okay, can you see the slide change?
The black. Wait for a minute.
The Zoom says it quit unexpectedly. Okay, can I restart my Zoom? Let me try again. Sorry, I'll just quit my Zoom and enter again.
Okay, sure. Well, let's wait for Chang to re-enter the room. Maybe we can start to some extra time for Q&A. Any questions for the previous two talks, the audience can type your questions in the web channel. I guess the webcast is also online on several different channels. So you can get ready for the Q&A session. Professor Haixia Zhang will also join the panel discussion very soon. Right, I can see our language is autonomously translated. So it's really how AI impacted science and technology and also the daily life, right? Now the translation is quite intelligent. You can do the real-time translation. Right, let's take a 1 minute break while waiting for Chang to come back.
Okay, sorry about that. Let me try again. Okay, so can you see my second slide?
Yes, it works now.
Okay, great. Yeah, let me restart from here. So yeah, so I think the first question. Oh, Zoom says again it quits. Why?
You can send your slide in the to me or to okay, it works.
It worked.
doesn't it crash on your end, or you can send the slides to the assistant so she or he can share from their end maybe. Great. Slide. Extend it. Let's wait for a minute. So it's a large file. Wait for a minute to see if we can find a way to share the screen. Professor Liu, maybe you can re-enter the Zoom and try again. Let's try. It's the third time, no more than 3 times to see if it works. Since the file is still being processed.
Can I try again? I just updated my Zoom.
Yeah.
Hopefully it works.
It works.
Okay, it works, and it works now.
Yes, it works.
Okay, great. Okay, I'm so sorry for this trouble. Okay,
it's worth waiting.
Hopefully it will
All right,
continue.
let's restart.
Okay, cool. Yeah, so I think the basic question to ask is why we care about the topic that I work on. So basically, we know that sensing and planning are 2 critical components to make a robot an intelligent robot. And basically, we are typically familiar with this path, which shows that first the robot senses the environment, estimate its on state, and then makes a plan for its behavior. So this we usually call the motion planning and control. And actually, there also exists an equivalent important path, which shows this path, which basically means that the behavior that the robot makes will actually affect the information it will senses. So basically, if we can plan our trajectory wisely, we can actually collect more useful information. So basically, this path is called the active sensing. So we can see that these 2 paths forms a cycle that actually are important for the robot to behave intelligently in an environment. And besides, in recent years, there's also an increasing interest in using multi-agent systems because these multi-agent systems have found many important applications, such as in logistics and also other applications. And so on this page basically shows that there are several important topics that are related to autonomous robots, and this actually forms the basis or forms the focus of my research. And to be more specific, my research has been focused on 3 topics. The first one is the optimal filtering for nonlinear systems. And in particular, we have developed the data-driven optimal filtering for nonlinear systems. And we have also developed the distributed Bayesian filter for multi-agent systems. And the second topic we worked on is on the safe online motion planning of robots. We have developed the safe trajectory planning approach for autonomous vehicles, and we have also developed the motion planning approach for robot swarms. And based on this work on estimation and also on motion planning, we have developed methods for on the active sensing for robots. And in particular, we actually study how we can make the robot autonomously find the targets of interest. And actually, this is a very typical task in the field of active sensing. So in today's talk, I will actually introduce some of our recent work on the following 2 topics. One is on the robot swarm motion planning, and the other is on the active sensing for robots, and in particular on the task of target search and tracking. Okay, so first, let's look at how we do this robot swarm motion planning. So as we know, robot swarms have been used in many applications such as logistics, search and rescue, and also other related tasks. And the motion planning is actually the fundamental capability for the robot swarm. So actually, there have been many works on the motion planning of the swarms, but these work are usually for the small scale of medium scale robot swarms. So when I say the small scale or medium scale, I mean the size of the swarm is usually around like tens of robots, like maybe 10 robots, 20 robots, or like maybe 50 robots. That's at most. But these kind of motion planning algorithms cannot be applied to large-scale robot systems. And when I say large-scale robot systems, I usually mean hundreds of robots or thousands of robots. So the motion planning of large-scale robot systems have become a very popular topic, especially in recent years. So actually, there have been some recent work on this topic on the motion planning of large-scale robot systems. However, these works either ignore the practical constraints of the robot systems, such as their kinematics or the collision avoidance constraint, or these methods lack flexibility in the generated trajectories. So it is still an open question on how we can actually do motion planning for very large-scale robot systems. So next, I'd like to talk about how we approach this problem. Before I talk about our research, let me take a look at how we actually formulated the problem of large-scale robot swarm motion planning. So as you can see here on the left side of this screen, we have several robots, and actually I want to mean like hundreds of robots. So they start from some starting area, and they need to navigate through an environment that are full of obstacles, and they want to reach this target area. So how can we do this in real time and also in a coordinated way? Well, so as I mentioned, there have been some recent work on this topic, but neither of them are really practical in practice. So our take on this approach is actually to view the swarm of the robot actually as a probability density function. So basically, when we view the robot swarm as the probability density function, now the problem is transformed into the optimal transport of the probability density function in the space. So now the problem is no longer making motion planning for large-scale robot systems. Instead, we care about how we actually design the optimal transport trajectory for the PDFs. And the benefit of this point of view is that this PDF, the complexity of planning the trajectory of PDF is independent of the swarm size. So this means that it doesn't matter if we have maybe 100 robots or we have 1,000 robots. The computational complexity of planning the trajectory for the PDF is the same. So by doing this kind of the transformation, or by taking this kind of perspective, we can actually develop methods that can have very good scalability and can scale to maybe thousands of robots. Okay, so this is how we actually do the motion planning for large-scale robot systems, but how we do that like rigorously or mathematically. So now let's take a look. So based on this idea of generating the path for PDFs, we propose our method, which is called the rover, and its full name is the Risk-Aware Swarm Robotics Motion Planner using conditional value at risk. So the basic structure of rover is like this. It is a hierarchical approach. It has two layers. In the upper layer, which we call the microscopic planning, it basically generates a path for the PDF to navigate in the environment. Then in the lower level, which we call the microscopic control, each individual robot will actually keep track of the trajectory of the PDF. So by doing this decoupling between the upper layer and the lower layer, we can actually achieve very good motion planning capability for the large-scale robot systems. And this figure, I think you can see this figure. So the figure on the right actually shows 4 time slices for the up-level planning. So here is the initial time. Here the black dot represents each individual robot, and this blue cloud represents the PDF associated with this robot swarm. So basically, this shows the starting state. And then by using rover, we can see that the PDF can actually navigate through this environment, and it can actually split into different subgroups, and also subgroups can merge into a bigger group, and then all the PDF can navigate to the target area. So now we actually have developed approach for the PDF to generate its trajectory to navigate along an environment that are full of obstacles. Then in the lower level control, each individual robot actually only needs to keep track of these PDF and then they can actually reach the target area. So this is basically how this rover works. And behind this figure, what we do is actually we actually formulate this model predictive control problem to generate a path for the PDF. So here's how it works. So for the PDF, we actually use Gaussian mixed model to approximate the PDF for the robot swarm, and then to evaluate how much cost this PDF moves. When the PDF moves, it can incur. We use the Wasserstein metric to measure the transport cost of the Gaussian mixed model. And to ensure that the robot swarm does not collide with any obstacles, we use the metric which is called the conditional value at risk, which basically measures the risk of collision when the swarm moves in the environment. Okay, so basically this tells how we actually formulate this model predictive control problem. But how do we solve this problem online? Well, actually, we utilize some very interesting results regarding the complexity of this conditional value at risk, and then we can develop a real-time motion planning approach to generate the collision-free trajectory for the PDF. But I will not go into that details in today's talk. So let's just jump into some simulation results. So here it shows the top row shows the results of our method. So this figure shows the trajectory of the PDF. As we can see, the PDF can actually navigate through these obstacles and move to the target area. And the left video actually shows the trajectory of each individual robot. And we can see that this individual robot can keep track of the PDF very well, and they can actually reach the destination very well. And we actually compare our method with 2 benchmark methods. Actually, there are 2 very representative methods for multi-agent systems. But both methods have some drawbacks that I will just not go into details. So here is just a qualitative comparison. We also compare our method with these benchmarks quantitatively. And here is the result. So I want you to pay attention to these numbers. So these numbers actually, so first, this number is the number of the robots in a swarm. So we test as many as 1,000 robots in a swarm. And for these numbers, for the numbers in this column, it corresponds to the total time for the swarm to move from the starting position to the target position. And this column corresponds to the time associated with our method. Okay, so the time in this parenthesis actually corresponds to the time for our method to generate the trajectory of the PDF. And as we can see that this time is actually stable independent of how many robots we use. So this actually corresponds to my previous claim that when we consider the planning of PDF, this computation complexity is actually independent of how many robots we actually use. So this is a very desirable property because this means that even we have 10,000 robots, the motion planning of the PDF trajectory will still be maybe below 1 second. And this is highly desirable in practice. Okay, of course, we have also other like better results than the benchmark methods, but I will not go into details in today's talk. So basically here, what I want to say is that we have developed a method to make motion planning for very large scale robots. And we actually have a follow-up work to this rover work because we noticed that despite the like good performance of rover, we still notice that the rover may not perform very well when there are too many obstacles or too crowded obstacles in that environment. So we combine our method with the PRM, which is a very, very classical method for motion planning in robotics community. And we propose our method called swarm PRM. And by doing so, we actually extend this classical PRM to large-scale robot systems. I will not go into details, but let's see how it actually works in simulation. So the middle column actually corresponds to the trajectory generated by the swarm PRM, and the right column corresponds to the trajectory generated by rover. Actually, their trajectories are quite similar, but we can actually notice that the swarm PRM can have better way to make the swarm pass through these narrow passages, while for the rover, the swarm will actually bypass the narrow passage, and by bypassing narrow passage, it will make the swarm move like longer trajectory, which is actually undesirable. So basically, swarm PRM is actually a better version for us to make motion planning for very large scale robot systems. Okay, so basically, okay, now the animation. Okay, yeah, so we actually have two places where there are narrow passages, and the swarm, when we use swarm PRM, the swarm actually can navigate through this narrow passage, but if we use rover, the swarm will just bypass these passages, which is undesirable. Okay, so here is our work, our recent work on the motion planning for very large scale robot systems. Next, I'd like to briefly introduce our work on active sensing, and in particular, on our work on target search and tracking. Okay, so when we say search and tracking, we actually refer to two operations. So when we say target search, it means that the robot does not know where the target is initially. So the robot needs to find a very effective way to find this target as soon as possible. And when the robot actually sees this target, now we actually enter the tracking stage. And because the target may be moving, so the robot needs to also follow this target and keep track of this target along the way. So this basically corresponds to two different stages. But what we do is that we can actually unify these two stages under the same framework. So basically, we have developed some approaches for this search and tracking in a unified framework, and we actually have shown that this method can actually work on different platforms, including this mobile robot and also this this quadruped robot. Oh, okay, the video is not playing. Okay, yeah, here it's working. So yeah, basically our method can work on different platforms and also works both indoors and outdoors. But when we finish out this work, we notice that traditional works that make the robot search and track moving targets, they actually only use the geometric information of the environment, such as they only care about whether there's an obstacle here, whether there's a tree, whether there's a box, but it actually ignores the very important semantic information that could actually help a lot in finding a target. So basically, later on, we actually work on a more interesting work, which actually involves a lot of semantic information. So basically, here is what we work on nowadays. We consider an indoor environment that are full of furnitures, and the problem now becomes the so-called object goal navigation. And interesting, we actually find that the AI community is also interested in this type of task, and this object goal navigation is actually what they call this kind of task. So here is basically what this problem is about. So suppose that we have an indoor environment. We place a robot into this indoor environment, and this robot does not know anything about this environment at the beginning. Now we tell the robot to find an object for us. For example, we want the robot to find a gray handbag. Now the robot needs to first explore this environment and then try to localize this object as soon as possible. And imagine that if we person do this kind of task, what we will do is that because we want to find the handbag, now the most probable places where the handbag could be is either probably in a living room or in a bedroom, and we may not want to go to the toilet to find a handbag, because it's very unlikely a handbag will be in the toilet. So this actually have some semantic information, or this kind of common sense is what the robot can utilize to more efficiently find an object. Okay, so given this problem set up, we actually propose a method to handle this problem. We call our method the Voronoi method. And in the Voronoi method, the full name of Voronoi is actually the Voronoi-based zero-shot object navigation with large language model. Okay, so basically Voronoi is actually a pipeline that includes perception, path planning, and control. And in particular, the large language models are used to guide the robot motion planning. And we actually utilize the common sense inference capability of the large language model to help the robot make better decisions about where it can find the object. Okay, so here basically shows the structure of our Voronoi algorithm. It contains 3 modules. The first is the semantic mapping module. Basically, because the robot doesn't know anything about the room at the beginning, so it needs to build a map on the way. So we build a semantic map when the robot moves along in the environment. And then we actually use the Voronoi skeletonization approach to build a semantic topological map for the robot to compress the information it has received from the sensors. Then in the decision-making stage, the robot will actually use both the map it builds and also the visual information, as well as the depth information it receives from its sensors. And then it will fuse a prompt to the large language model and to ask the large language model which way it should go next. And once the robot decides which path to go, then it uses a local policy module to actually move to that location. Okay, so this is basically the pipeline for the Voronoi. I want to emphasize 2 parts of this algorithm. First is that we use the Voronoi skeletonization technique to construct this semantic topological map. Actually, the Voronoi map is a very typical approach traditionally used in motion planning community, but nowadays in the AI robotics community, they don't seem to use it a lot, but in our research, we noticed that when we use Voronoi representation, we can actually help the robot better understand the environment in a more efficient way. And the second thing I want to emphasize is that our Voronoi approach has zero-shot characteristics, which means that it can recognize objects it has never seen before, and that our algorithm can actually be deployed into a very new environment without any fine-tuning. Okay, so that's enough for the technical part. Now let's see some videos. So here basically shows the video of our Voronoi approach. So basically, this is environment, this synthetic environment that people usually use for this kind of tasks. So as we can see that when the robot moves inside this environment, it actually builds a map at the simultaneously. And in this map, we notice different colors. So these gray parts represent the obstacles. These light gray parts represent the free space where the robot can actually move. And we also notice some colorful parts, and this part actually corresponds to the sink that the robot recognizes. So basically, the robot will recognize some objects when it moves and it builds the semantic map. Okay, so here's the first time the robot asks the large language model. So basically, the robot says, okay, now I'm at this point. I can go to 2 different places. And then when I go to the first area, there will be a bathroom with a door. And when I go to the second area, there will be a bathroom with a shower head, and I will pass by a sink. Okay, so then the robot asks the large language model if it go to area 1 or area 2, what's the probability that it will find a sofa? Basically the goal object in this task in these 2 different areas. So the large language model will answer in area 1, it will have like 0.2 probability, and in area 2, it will have like 0.05 probability. So the robot will go to area 1. Okay, so when the robot moves to area 1, it will see more information. So it will continue building this map. And then when it moves to another critical point, it will again ask the large language model. So basically, by the robot will actually like continuously build the map and sporadically or occasionally ask the large language model to help it decide where it needs to go next to find the goal object. Okay, now it actually has 3 different places to go, and it will ask the large language model. So for the area 1, which the large language model think there is the highest probability of having sofa, this area 1 actually has a bedroom with a couch, a bed, and the pillows, and the robot will actually pass by chairs on the way. So yeah, this actually looks like there will be a sofa in this area. So the robot will actually move into this area. And as you can see, the robot will recognize different objects when it moves, and finally, it finds the sofa here. Okay, so this is basically how this Voronoi actually works in practice. Okay, oh, I noticed the time is close, so I will speed up a bit. Okay, so this is how we develop our method for this object-go navigation, and we'll actually evaluate both qualitatively and quantitatively. And actually, to help develop methods for this type of object-go navigation, we actually also develop our own data set, which is a new data set for open vocabulary zero-shot object-go navigation tasks in dynamic environments. It actually has several features that are very different from existing public data sets. And actually, we have released these data sets recently. I will not go into details, but I just want to emphasize that this data set is quite challenging for this task, and we test several state-of-the-art methods on our data set, and they all don't perform very well. This means that our data set is pretty challenging, and actually our data set is very similar to, it's closer to reality than existing public data set. So I think it's worth trying this data set if we want to develop methods on the object-go navigation. Okay, I will skip these slides. Okay, so I think I will quickly wrap up. Let me see. Okay, so basically in today's talk, I briefly introduce our two recent works. One is on robot swarm motion planning, and one is on the large language model-driven active sensing. And I think the idea is that with the advancement of more or with better or more powerful techniques from AI, I think the robot can become more powerful, both individually and also as a group. And that's all for my today's talk, and I'm happy to discuss more later.
Thank you very much. Really enjoyed the nice talk with rich content. Right,
Oh,
thanks
Professor
again.
Wang, I don't think I can hear you. Is that my problem?
I can hear.
Oh, probably that's my problem. I see Professor Fang is also talking, so.
Yeah, I'm not sure what happened with the problem.
Oh,
I
okay,
think it
okay, I can
works
hear
now.
you now. I can hear you now, yeah, great.
Okay, great, fantastic. All right, hello everyone. Thanks for excellent talk by Professor Liu and Professor Fang and Professor Wang. So we had a wonderful night experiencing the advancements in artificial intelligence and the robotics. Now let's have a 20 minutes for panel discussion and Q&A session. Unfortunately, Professor Zhang cannot join us, so I think this is our panel today. I can see our profiles on the big screen. All right. So I think first of all, we really appreciate the different angles the three speakers brought today, from fundamental theories, mathematical foundations, towards the application merits. Right. So to start with the discussion, I think there were warm discussions on the platform, but there's no specific question to anyone. But there are a lot of discussions because people are really interested in this area. Maybe I can start with the true challenges in the field, right? We have seen a lot of advancements in robotics, also on news. As who I'm not a professional researcher in this area, but as a kind of user of robots in life and sometimes of our research. Now our chemistry laboratories are also using the robotic arms, so we are like the adopters of the technologies. So we do hear about what are the in your mind, what are biggest challenges? Maybe the first question to discuss, right? What's the biggest challenges? I heard the last part Chang shared about the data side, right? I also heard the data side is very important to lead the field. But what's the exact form of the data side needed in the area, and how we can build up this kind of open data and open challenges to advance these areas? So that's a first non-expert question. Maybe Chang can address certain
Sure.
first, and then we move to Professor Fang and Professor Wang.
Sure. Yeah, I think that's a very important question. Everybody is talking about data nowadays, and I think it depends on what kind of applications you are using. Because nowadays, when we talk about data to train a robot, we usually focus on we actually, like, for example, if we want to use manipulation data, we actually collect a lot of data on the manipulation tasks that are related to your application, and then we train the robot. So for example, if you want to do a chemical experiment, probably you want to collect a lot of data where the humans actually collect the data of how humans actually do these chemical experiments. Then the robot can learn from this expert data and then develop their own manipulation skills. But I think nowadays there's a trend to develop more general purpose manipulation skills. I think Professor Fang especially is an expert in this area. So basically, maybe hopefully in the future, the robots, when they are trained with enough data, they can do all kinds of manipulation like tasks. Yeah, Professor Fang, do you want to give some opinions on that?
Yeah. I strongly agree with Professor Liu, and I focused on robotic manipulation more than 10 years, and without artificial intelligence, we use some methods like automation to control a robot to implement some tasks, some manipulation tasks, and nowadays, while embodied artificial intelligence is so popular or so hot because we realized that the robots not only have a brain, but also should be has a talented body. And in my talk, I also focused the tactile because in our manipulation, we not only need the visual information, but also we need the tactile information. But nowadays, the tactile intelligence is lower than the vision. So because of the tactile sensors is not so famous, it's not so mature. So we were trying to improve the talent of the body, the robot's body. So we developed some intelligent tactile sensor integrated with visual information. We really want to integrate the multimodal informations to improve our manipulation skill. So yeah.
Yeah, I guess in video field also a lot of similar thinking.
Yeah. So in video field, for example, for our research, so also data is very important, but so it's a little bit different because actually when the video is actually the final receiver is a human. So basically we need the labeling from the human, and basically we know that different human have different opinions. So but now we also focus on the when the video, so the receiver is a machine. So for example, different robotics. So basically, different receiver, for example, robotics may use different algorithms. So basically, but so how we could generalize our model to meet different demands of different receivers. So that's also very important. So it means that basically when we collect the data, we not only consider the real application scenarios, but also we need to consider something unseen. So basically, for example, when we do the machine learning research, so we have a related field which is domain generalization. So not only adapt one domain to another domain, but also adapt to the domain that has not just assume that it's not being perceived or has not been explored. So we need to consider this case as well. Yeah. Thank you.
Excellent. I guess open data have advanced the field a lot. Also, the second question, I think everyone is also very interested in and the research a lot on how large models, not necessarily large language models, but kind of large scale foundation models impacted different areas. I also heard a lot of discussions from your three talks about how we quickly adopt and even develop some large models in each of the area. But how is this so fast, right? The development so fast nowadays, and how it really impacts all these different areas. Could you share some expert opinions and also to guide some directions for the younger researchers? Because recently during our PhD defense, we found that many of the tasks students have been researching for several years can be fully done by large language models. It's kind of a big shock to the students, but for this kind of era of large models, how can we adopt them, or how can we even combine the strengths to our fields? Maybe Professor Wang, we can use the inverse order, so Professor Shiqi can start.
Okay. Yeah, okay. So basically, I think how to define the large model, how to define this large. So there's no kind of conclusion, but maybe today's large model in the future will be a small model. But from my own opinion, but this opinion may not be correct. So basically, we need to, for example, for our video research, visual research, we need to capture the essence of the data. So instead of using more parameters but using more parameters to kind of train the model to build the model is good, but how these kind of models could capture the essence of the data. So I think all the nature of the data, so how the data is generated, because when I was a PhD, so basically there's not too many work on this kind of neural network, or I didn't read too many papers on that. But basically, our research is work on the with them relevant to the natural scene statistics. So using the equations to describe the natural scene, but not this kind of. But nowadays we know that now we use the large models. So I believe both are beautiful. But so maybe how to combine them. So it's also interesting. So that's some of my thinking. Yeah, thank you.
Thanks. Professor Fang, do you have any opinions? I saw you developed RobotGPT, which is quite powerful. How can you quickly?
Okay, thank you. It's a good question. And just recently, I just finished a paper that what the foundation models can bring for robot learning in manipulation. And I focused this research about 1.5 years before, and I think it's a brighter future, and this new technology, or it's also a new tool for the robot. So not only me, but also Professor Liu has also a greater work integrate the large language model for robots. So I think this new era or robot age, the foundation models is an acceleration for enter our society to the robot society. Yeah, thank you.
Excellent, thanks. Professor Liu, any side?
Yeah, so I think in terms of the size of the like large models, I think there's no general rule. I think because it depends on the area you use that. For example, when we talk about like the text or natural language processing stuff, like GPT, like maybe 1 billion, we already have like very good performance. But when it comes to the region applications, it seems that even we have like maybe 1 billion parameters for a network, but the data itself may be very sparse in terms of the useful information. So that's why in GPT or large language models, we see the emergence or the emergence phenomenon in these language models, but we don't see this emergence in vision models. And I think it's still unknown why this doesn't happen, but the speculation is that the vision information is pretty sparse. It's not as dense as text. So I think when on one side we should have a large model. Maybe the bigger the better. If you don't care about how we train that, maybe the bigger the more parameters, the happier. But another side is that it depends on what data we have, and even we have a small we have like a network with 1 billion parameters. Can we have high quality data to utilize the full power of this network is also very important. So yeah, so that's basically my opinion is that the bigger is the better, but we also need to think about the data. Yeah.
Right, indeed. Professor Zhang is online again, so we discussed
okay,
the challenges.
hello everyone.
Hello.
Yeah, hello everyone. So happy to listen to these 3 wonderful talks. Actually, I'm on my way back, so yeah, it's a little bit of trouble here. But yeah, also actually recently I'm really interested in AI, so I'm happy to see software, hardware, and hybrid. Yeah, so 3 of you here. So I want to ask a question maybe related with the previous one. So in your opinion, for the future of artificial intelligence, software, hardware, and this hybrid, which part will be the most challenging part? Which one will be the, 卡脖子 like this, bottleneck? Yeah. Okay. Anyone who goes first?
Ms. Fang can start.
Okay. Yes, it's a great question, and I think it's not only or software or hardware, but I think the big challenge is the combination, and also the different background should be work together or cooperation to push the artificial intelligence technologies improvement. So it's hard to say the software or hardware, but in my opinion, the cooperation and the combination of hardware and software is the most important factor in the development. Yeah, thank you. Okay.
Yeah,
Anyone else?
I also agree with Professor Fang. Yeah, actually, I think as you can see nowadays, like when we want humanoid robots or when we want like four-legged robots, actually there are several companies in China that can build a very good head hardware, and we also have a lot of companies and as well as universities that can like develop very nice algorithms. But I think the more important thing is that when one side is pushed to the limit, if we want to improve the performance any further, we probably want the other side to help. So basically, I agree with Professor Fang in terms that we need to combine, like we consider both hardware and software in tandem, and then develop them like together. Yeah.
Yeah, I also agree with that. So because hardware and software, so in my area, so it's coupled. So when we develop the algorithm, so basically we need to consider the hardware as well. Yeah, thank you.
I just
Okay.
add a quick
Yeah,
note
this
to that.
question also go to Hi, Xiaodan. This question also goes to you. So I think software, hardware for this company, but without the power, nothing. No,
Yeah,
you related with
exactly.
energy, you know, for AI. Yeah.
Yeah,
So what's
yeah,
your
exactly.
opinion for this?
Indeed. So we normally study AI for energy research to discover the high energy efficiency, electrolyte, membrane, and batteries. And also we study energy for AI, how we can have higher energy efficient algorithms and also hardware. So it's always a type of problem. But I also want to appreciate what I learned from the talk today. I think I heard in the first and in all the talks there about sim to real techniques. This is so important to our field because the data in our field is very expensive. Almost in all scientific field, data is very expensive because we do one round of experiments. It takes time and money. So we normally do some simulation and some digital twin techniques. So the simulation environment, where we transfer this domain knowledge to the real environment, this sim to real process can play a significant role. But we have not identified kind of a general or effective approach to do this. But I learned a lot this new advancement today, and hopefully we can collaborate on this point so that bring this advancement in AI to industry. Because I feel that the AI area is advancing so fast, but the adoption of those technologies are far behind. So we do have the responsibility to use these technologies. Yeah, thank you, Professor Zhang. I think time is
Thank you
almost
very much.
there, right? Professor Zhang, if you have any final notes, I think one last minute, maybe we can leave to the three speakers today if they have any message to share with the audience, or if you want to talk to the younger students and researchers to share some message.
Yeah, that's also my questions for three of them, you know. So as AI was a young generation's, you know, kind of field, right? The future. So what's your words passed to these younger generations? Please, who'll go first? Shiqi, maybe start from you.
So I'm from computer science. So but I believe so AI plus X is the future. Yeah. So yeah. So I actually believe that. Yeah. Thank you. Thank you.
Professor Fang.
Okay.
Yeah. My background is complex. I learned mechanism and computer science. So I think in artificial intelligence age, I think we really need more deep, and we should know we should cooperate with different background. So I think cooperation is very important. So okay, thank you.
Yeah, I think my background is very interdisciplinary. So I think the message is that we need more people to learn AI, and we want people to bring the AI to different areas because AI is a very powerful tool. But we still need more people to explore the frontier of where the AI could be used in various disciplines.
Great.
Okay, great.
Professor Zhang, you have any final words to share with the audience?
Yeah, so I mean, it's really great. Actually, I just realized that today we have the strongest team, yeah, from Tsinghua and from Beida, Yeah, you realize that? Yeah, Shiqi was a graduate from Beida and also different background, in different countries, so in different areas. So really, really good. I happy to, have more young talent in this stage and hear more about that. Okay, congratulations. So Xiaonan, please go ahead.
Thank you very much. So now that comes an end to our technical program, and the last step is to show our certificate to the 3 distinguished professors to show our appreciation as a panel member, and also sharing your research and opinions for young scientists shaping the future. So on screen shows the certificate for the 3 speakers
Thank you.
today. Thank you very much. Thank you again
Thank you.
for your contributions.
Thank you.
With the audience to warmly appreciate your time and excellent sharing. All right, then I think there is some slides for some events. Right, Professor Zhang, you want to say some words about the Davos Summit? This is a very famous event worldwide with
Yes.
excellent speakers.
Yeah. Thanks, Xiaonan. Actually, Davos, ICAX Davos Summit will be in July. In the summer, this will be the first time for the ICAX family to go together. So welcome all of you to jump in this big party. So the keywords here is innovation, science, technology, investment, management, and entrepreneurship. Short for it's time. So it's time to go summit. Welcome.
It's time to go to Davos to experience the frontier of science and technology. Let's join Professor Zhang together. All right, so this shows the next youth talk. So this event is every week, right? If the new audience here, you can join the platform. I bet you will learn a lot. I really enjoyed all the sessions in all the series of talks. Okay, I think that's comes an end of our youth talk today. Thank again to all the speakers and the organizers today. We really had a wonderful night before the May holiday. So wishing everyone a pleasant break. I guess you will work anyway, but I hope everyone enjoy the future of artificial intelligence shaping our life and the future, and enjoy our research and science. Thank you very much. Thank you.
Thank you.
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 ICANX 达沃斯科学峰会。那今年是第1次 ICANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第1个是创新 innovation， 第2个是科学 science， 第3个是 technology 我们的技术，第4个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来就是 It's time 是时候了，是时候让我们去达沃斯听这些非常给我们启发的关于未来的这些报告。在达沃斯我们会有3个非常重要的论坛，一个是诺贝尔奖论坛，我们会邀请诺贝尔奖获得者来跟我们谈科学的未来，我们会邀请世界科学院的院长来跟我们谈世界科学技术发展的未来，那我们会邀请大学校长来参加我们的世界大学校长论坛，来跟我们谈关于教育的创新教育的这样的一个未来。同时呢，在达沃斯呢，我们也会邀请各行各业的这样的一个非常重要的领袖人物、领军人物来跟我们分享他们的所思所想，他们对未来的思考。那我们也会邀请非常多的各行各业的精英来跟我们分享他最精华的这样的一个思想。那当然了，达沃斯这个舞台也不只是给这些大牛们展示的舞台，也是我们来展示的这样一个舞台。所以如果你有好的故事、好的思想、好的技术、好的思考来进行分享，那也欢迎你再来线上投稿。所以我们的截止时间是4月1号，大家还有1个月的时间来准备好你的发言，希望分享给全世界的。所以欢迎你在线提供你的资料。那我们也希望你成为这个舞台上的明星。那在达沃斯呢，我们设了3个奖。第1个是针对大学生的，你是创新创业的最牛的大学生，那你来申请我们的创新奖。如果你是一个毕业10年以内，现在正在从事独立科研工作的科学家，那你来申请我们的青年科学家奖。如果你是一个创业者，你成立了你的公司还不到5年的时间，已经发展得非常好，那请你来申请我们的创业奖。所以所有的奖项申请的时间截止都是4月1号。那欢迎大家在线提供这样的一些资料，那我们也会给大家非常多的这样的机会，成为舞台上最亮的星。那是时候来我们大家一起把科学推向未来，推向世界。那这个呢是我们在达沃斯的非常重要的合作伙伴，我也希望你成为我们的合作伙伴，我们一起来推动世界的发展。那现在达沃斯论坛已经开始注册了，所以各位朋友、各位好朋友们，请你们开始尽快注册吧。我们相聚在达沃斯，我们一起 Go Summit 走向巅峰。
在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待。技术革新浪潮汹涌而至，对其高性能的需求、无限小型化的追求，成为行业发展的必然趋势。多层陶瓷电容器、电感器、高可靠性元器件、太阳诱电支撑其全流程的先进技术，提供给用户全方位的服务。为了科技的发展，我们一代代太阳诱电人肩负使命，激情拼搏，以极致的